Good morning. Welcome to DVCon and to this workshop on a standardization effort of the Accellera Function Safety Working Group. I'm really glad we have the opportunity to present the progress the group has made so far and what our plans are for the future. I'm the chair of the Functional Safety Working Group, and I will only be giving you a 1-minute introduction to the mission and to the initial objectives of this effort. So here you can see how the workshop is structured. Oscar Balan, Senior Principal Architect at Eternovia, will start the workshop by presenting the requirements we gathered from the community. Om Ranjam, Principal Engineer at ST Microelectronics, will cover the work that the group has been doing in defining a functional safety standard. And Gani Kanawati, Technical Director at ARM, will close the workshop by describing some of the future directions we are exploring as a continuation of the initial part of the work. So in a nutshell, the group has identified 5 challenges to start with that are summarized here to the left. So Oscar is going to go and describe all of this into details. So these challenges are all related to how to capture, store, manipulate, exchange functional safety data to support the best practices and guidelines of safety standard, for example, ISO 26262 and IEC 61508. And the goal for the Accellera Functional Safety Working Group is to improve, as you can see here to the right, the interoperability, the traceability, and the automation of the development process of safety critical applications. So our first objective has been to provide a functional safety standard that would accompany the traditional design standard and support the need of the functional safety of the safety critical life cycle. So the first step has been to find common ground in the best practices and methodologies across the industry. And then we started to define the functional safety data to enable the data exchange and manipulation. So will cover this in great detail in the second part. So this has been our first initial focus, but in parallel, more topics are considered for exploration since they are related to and influence the way the functional safety model is defined. And Gani will cover these future directions in the last part of the workshop. So Oscar, and Gani, thanks a lot for all the work in the group and for presenting today at DVCon U.S. One last point before we move on with the rest of the presentation is actually a specification about the type of work that is presented here. We were very keen on presenting the update on the progress we've made and the projects we have, but please consider everything that we are sharing today work in progress, as the group is very active, a lot of discussions are ongoing, and things will probably actually change and progress as we move along. So just a caveat as we move along with the rest of the presentation.
Hello everyone. In this presentation, I'm going to show what are the motivations of the Accellera Functional Safety Initiative, who are the stakeholders, and the overall scope of the activity. As we know, the ever-growing implementation of electronic systems for safety-critical application is posing a growing risk associated to the possible failure of such systems. The definition of functional safety standards such as ISO 26262 for the automotive industry or IEC 61508 for the industrial application and other standards is made with the intent to give a guidance to the suppliers of those systems on how to mitigate those risks during the product life cycle. In this context, Accellera formed a working group of functional safety practitioners and experts with the intent to develop a standard aiming to provide a consistent definition of the functional safety data to be exchanged among different actors of the industry in order to improve automation, interoperability, and traceability. The standard aims to specify a data model, language, or format in order to exchange data seamlessly among functional safety artifacts and across the different layers of the supply chain. To achieve functional safety of an entire product, such as a car, for example, or an aircraft or an industrial robot, The system and all its components are developed taking care to avoid or mitigate all the major risks associated to possible product malfunctions. All the parties participating in the system development, the supplier of IPs, components, modules, and the vehicle or robot itself, must all work together to achieve safety goals identified for the system in order to minimize such risks. The problem is that such a collective effort is distributed among different companies who therefore need to coordinate their outcome in order to ensure consistency of the safety goal of the final product. The life cycle of the development process of safety-related products requires the generation and the management of interrelated categories of information at all development stages. This information may be generated in diverse formats using a variety of electronic design automation tools and originate from all the various suppliers participating in the product development. Despite having a myriad of sources, all this information must be integrated and exchanged among different organizations while maintaining their integrity and consistency throughout the whole supply chain for the achievement of the functional safety goals of the complete product. The objective of this standard is to foster the exchange of this data between organizations and tools with high integrity and traceability. Here is an example of activities and work products possibly associated with a safety product from the perspective of different suppliers. Starting from the bottom of the table, the IP and the component suppliers develop their product out of context, that is, knowing the reference market, but most of the time without the knowledge of the specific application their product will be used for. Because of that, for functional safety, they used to do a bottom-up analysis, starting from the basic fault models of their technology. As a result, for those suppliers, the definition of the safety requirements of their product is associated more to the reliability of the function declared in their product specification, rather than to real safety goals whose violation could harm someone. It's up to the module and final system suppliers, then, who are integrating the IP as a component and who have the partial or full visibility of the possible bad consequence of a failure, to put together this information in a coherent manner, consistent with the safety goals of the final product. We can see that not only it is needed to link the outcome of the different companies composing the supply chain, but also inside the same company many different work products are being produced and needs to be stitched together to form a coherent safety case for the subsystem they supply. This poses an opportunity for standardization that should result as an advantage for the whole industry. Consequently, the Accellera working group has defined the following objectives: to define functional safety data content needed to support activities and work products generation from IP to system level in both interlayer and intralayer use context. To define a language or a format or a channel to exchange this information across distributed development environment of the functional safety lifecycle. The standardization of data exchange will result in advantage for the suppliers at different levels of the supply chain who need to exchange and have traceability on safety requirements, safety analysis, verification evidence, etc. It will be an advantage for the system owner who owns the safety case of the whole system, is the one interacting with the public and regulator, and is the first actor involved in case of lawsuit. Therefore, has all the interest to achieve clarity and completeness of the evidence supporting the safety case. But for this very same reason, it is also in the interest of the rest of the industry that the data and their structure are crystal clear for the system owner, in order to avoid to involve the system suppliers in case of lawsuit due to lack of data clarity. The standardization of data and of work product structure would allow a better review of the work product provided by a supplier to their client. If it is clear from the beginning what is the expected format of the evidence that will be given. This in principle is true at all levels of the supply chain. Let's imagine a Tier 1 who needs a set of work products and data from different silicon vendors as evidence of the definition of safety requirements for the semiconductor components used at system level, their safety analysis and the verification evidence. Currently, the format is left to be defined by the suppliers, or in some few cases the Tier 1 is in the condition to define them in advance with their suppliers as part of the technical negotiation. In both cases, the integration requires an effort that could be quite reduced if the format was a given from the start for every actor involved. If we look at the issue from the semiconductor vendor perspective, today there is quite an effort spent to explain the format of the data provided to their customers, show their completeness, and in many cases customize their format depending on the customer needs. This is the case for semiconductor vendors, but also for any suppliers like IP vendor, Tier 1, or even EDA vendor. Most of this effort and unnecessary variability could be saved if the data and work product format was defined from the beginning for everyone. An important aspect of managing functional safety development is the requirement for traceability of information, that is, the ability to have an origin and a course of development to follow through the chain of requirements and modification that a product goes through. This holds true for both intra-layer and inter-layer management, but can be especially challenging when different actors in the supply chain are involved. In case of a liability case, for example, traceability is key to identify the root cause of the accident. On a more regular basis, traceability is also required to perform an impact analysis, which relies on a solid change management system. Similarly, it allows for verification and validation of requirements as captured in the video model. Another example of the need of recorded and documented information are the assumption of use involved in the development of a safety element out of context. That is the definition of safety requirements by the component vendor to their customers in order to preserve the safety of the component during system integration. The functional safety standards requires to maintain and demonstrate traceability of the safety data across levels in the supply chain and among work product, with information justified, documented, and preserved for years in a safety case. Although several products and strategies are available to aid the ability to trace information, a full holistic approach is not available, and no negligible portion of the safety data exchange is handled manually or ad hoc, leading to an error-prone and effort-intensive solution. A clearly defined and standardized format for the exchange and integration of functional safety data can significantly improve the efficiency and confidence in the integrity of the development process. To recap, the mission of the Accellera Functional Safety Working Group can be summarized in these three characteristics of the development process: interoperability, traceability, and automation. The goals of the Functional Safety Working Group are to unify and standardize the methodology to exchange functional safety data for functional safety activities, such as analysis, verification, validation, optimization, implementation, to produce work products such as FMEA, FMEDA, assumption of use, fault tree analysis, dependent failure analysis, safety requirements. Define a language format to exchange the functional safety data across the distributed development environment of the functional safety lifecycle. The scope of this effort develops across several dimensions. These are illustrated in this slide, but it is not meant to be an exhaustive categorization. The green boxes define the scope of the Functional Safety Working Group and capture how the work will proceed in phases. The immediate focus aligns with the content below the dotted lines, while the content above is planned as a next step.
Hello everyone. In this presentation, I will talk about challenges in the domain of functional safety and then about the work being done in Accellera Functional Safety Working Group to enable the community. Functional safety data and the scope. What is functional safety data? We at Accellera Functional Safety Working Group define functional safety data as the information needed to perform functional safety operations and generate the associated safety work products. The goal of such standardized safety data is to enable interoperability and traceability across work products and processes within a development level or across the supply chain, that is intra-layer or inter-layer. Such data should allow to develop an industry-wide functional safety aware flow to bridge the gap between the well-established methodologies for design and verification of the products and the ever-growing requirements for safety work products, covering different domains, industries, and the supply layers. I would like to highlight that the goal of this exercise is not to standardize example functional safety analysis format, which is already covered by the existing safety standards, but to enable the realization of the requirements of the standard. A layered approach has been adopted for the development of the functional safety content standard, where the focus is to identify and agree on the content first as part of the conceptual data model. The conceptual data model then drives the language format of the functional safety data. Similarly, scope is layered based on dimensions, namely work products and activities, industry segment governed by the relevant safety standard, and the domains like digital hardware and others to follow. The scope of the data model activity is spread across industries, domains, and stakeholders in the supply chain over the safety work products. Current efforts are focused on enabling the automotive semiconductor industry in the safety analysis, primarily FMEDA, by standardizing functional safety content. The engagement targets silicon, example system on chip, discrete but medium to high complexity components like analog to digital converters, digital to analog converters, sensor modules, etc. Subsystems composed of multiple intellectual properties and intellectual properties. Subsystems and IPs include RTL and hard macros, while SoC refers to manufactured silicon. Traditionally, in automotive sector, safety processes had been native to the system and vehicle developers. Thus, the risk was better controlled. With the proliferation of complex electronics into safety systems, the development has become distributed. This has increased the underlying risk and shared responsibilities. Development of the safety analysis report for use by the end customer is long, arduous, and not so well defined for developers and integrators at each level, that is system, silicon, and intellectual property. It is much bigger effort for the integrators to create a consistent and reliable output from inputs originating from diverse suppliers, that is, the interlayer communication. System integrators have to deal with varied information like faults and failures from diverse suppliers. Suppliers have to fulfill requirements coming from different integrators. The product has to comply with multiple safety standards when serving diverse industries. The intra-layer safety analysis has to evolve consistently, accurately, and reliably during the development phase. Broadly speaking, uncertainties and inconsistencies get added to the safety activities while going parallel to the evolving product development with increasing details at each level, and moving from qualitative FMEDA to quantitative FMEDA with failure rates and failure modes. This reflects the complexity of identifying and classifying the functional safety content for the data model necessary for harmonization of the safety analysis at inter and intra-layer. Functional safety data model shall capture and classify all the information needed to realize the different safety processes and the work products. It shall include all data independent or related to other safety work products within a layer or across layers. Independent data like failure rates, interlinked data, for example, between FMEDA, DFA, and safety manual. At present, focus is on FMEDA of IP and component. The definition of layer has been redefined in Accellera case to be generic for global relevance and hence to fit different standards. We will now reflect on activity of the working group towards the functional safety data model necessary to harmonize the industry-wide effort on safety analysis at inter and intra-layer. The task related to FMEDA data model has been layered into 3 steps. First step has been to arrive at a consensus on a generic approach, which serves the concurrent practices and flexible enough to serve the currently foreseen methods in future as the product development methodologies and technologies are evolving. Formalization of the functional safety analysis process is the first step which should lead to development of the conceptual data model. Finally, the activity shall culminate into a data model language which should enable interoperability, traceability, and automation. So far on the safety analysis data model, work has been done on an assumed common workflow for FMEDA, foundation concepts, process formalization, and hierarchical or interlayer FMEDA. Based on current practice and inputs from the members in the group, a common workflow has been agreed as the starting point. The analysis starts with a hardware model which can be hierarchical. It may also be a structural representation with physical attributes like gate and area information. The final version is always a hardware structural model with physical parameters. The hardware has an associated failure model which contains the failure mode definitions and base failure rate information from technology. Each failure mode of the instance has attributes like safety relevance, associated safety measures, and the corresponding diagnostic coverage. In user-specific safety scenario, the failure modes are mapped to the safety goals or the functional safety requirements. For this detailed analysis, summary report is finally generated. Some of the basic concepts behind the safety analysis have been at the core of the activity in the last couple of months. So the basic concepts are FMEDA types, mapping between hierarchies, representing and connecting information, functional safety model elements and attributes, and finally safety mechanisms and the diagnostic coverage representation and aggregation. For sake of clarity in the context of data model definition, two types of FMEDA have been considered. Assumption-based FMEDA, where design metrics are estimated by the user. Second, calculation-based FMEDA, where design metrics are derived from design hierarchy and related data on area. The calculation-based FMEDA is performed after design mapping. And final FMEDA is calculation-based as far as possible, but can also be a combination of the two. The rationale for the distinction is that when the functional safety hierarchy and the failure mode hierarchy are linked or associated to the design hierarchy, the total area and failure mode distribution are not assigned by the user, but are derived from the design hierarchy, and care must be taken to not introduce inconsistencies in the data model. The distinction here is not about accuracy. Two hierarchies may be related by a mapping function, where each hierarchy is a separate, pre-existing data tree structure. Mapping links are then placed between elements in each tree. Not one-to-one mapping is also possible by combining, partitioning, and repositioning in the tree. Mapping between hierarchies could mean functional safety analysis, hierarchy and design mapping, and safety mechanism and design hierarchy. A design may be represented in different but equivalent ways, like block diagrams and trees. This representation must be mapped to hierarchy, matching with the granularity of the safety analysis. For example, two instances of a design may require to be analyzed at different granularity and thus require different mapping functions. This slide represents the data view mapped to the functional safety analysis process. The process representation is indicative of the state of activity at present and not the complete process. The process starts with analysis of the intended functionality of the design from safety requirements point of view. It selects the design depth for safety analysis and assigns the safety relevance. Subsequent step assigns the ways in which each leaf of the functional safety analysis hierarchy can fail to create a failure mode hierarchy. A conceptual data model is being worked out where high-level categories for information are being defined. Also, efficacy of the defined categories of information to allow development of the FMEDA using different approaches is continuously evaluated. The assumption-based FMEDA flow is based on lack of availability of associated design hierarchy. What we see here is the paths of the FS data, which is relevant for assumption-based FMEDA. The calculation-based FMEDA is derived from the computation of the failure rates and diagnostic coverage from a structural design. So what is in the pipe for the future? The next steps are create some test examples of safety analysis and test data formalization. In order for wider coverage of the current practices and comprehensiveness of the model, Reviews and feedbacks will be arranged with the developers and integrators of the model. In parallel, continue with development of the conceptual data model with more details. And finally, define a data model language for the conceptual data model. And also to extend the model to cover other safety-related industries and safety activities and the work products. I would like to thank all the listeners and also the members of Accellera Functional Safety Working Group. Let's remember, safety first.
Hi everyone, my name is Ghani Kanawari. I'm going to be talking about the Accellera Functional Safety Working Group future topics. The topics shown in this figure are the scope of the Accellera Functional Safety Working Group. And as can be seen here, some of the topics which I highlighted in darker color have already been covered by my peers earlier: the safety analysis, the data model, the safety standards, intra and interoperability. Now, the remaining of this presentation, I'm going to be focusing on the one that are in the lighter color, which is the assumption of use, safety manual, reliability and availability, safety case, and the verification and validation. Those are the new topics that we are planning on working them in the future. I borrowed this slide from Oscar from the previous presentation, and I'm not going to spend too much time on it because pretty much he covered most of it. But I just want to mention that in the past year, our focus was on the automotive markets, specifically the ISO 26262 standard, safety standard. But the plan from the beginning that we're going to cover pretty much most of the safety standard, and I'm listing here a few of the ones that will be our focus for this year and next year. Next topic will be the reliability and availability. Reliability, availability, safety, maintainability, and security are several topics under the big topic of dependability. The definition of dependability is the quality of a service that a particular system provides. In the Accellera group, Functional Safety Working Group, we have been working with safety or on safety for the past year, and we continue to work on it this year and most likely for the future. But at the same time, since the beginning, we know that we should have to cover both reliability and availability. We don't have any near-term plan to cover maintainability and security. Now, reliability and availability and safety, they are kind of very close together. And for example, today, most safety products are considered to be fail-safe. But in the future, especially when you go to autonomous driving level 3 and above, availability becomes very important. So we need to make sure that whether it's the data model or the interoperability or intraoperability satisfy the availability topic in terms of data fields or communication and so on between the different layers. Similarly with reliability and safety, today, for example, you could easily design a product for safety markets, but later on you want to use that same product for reliability, and instead of starting all over again, there are many data or commonality that you can use between those two different fields. And in order for that to happen, you want to enable your data model and again the processes that we have defined so far for safety also to satisfy availability and reliability. Next topic is assumption of use. The assumption of use are used in safety element out of context development, where the producer of those assumptions lack the requirement or definite requirement from customers, so they use their own assumptions about those requirements, which later have to be verified by the consumer to make sure that it meets their requirements. The lack of defined common format for those assumptions make it a heavy burden on communicating those assumptions across the different layers in development. And also today, there's no way of tying those assumptions back to existing requirements. The plan for this working group is to define or agree on a common format for specifying those assumptions and identifying methods of how an assumption is validated by the consumer or the integrator, and define responsibility between the producer and the consumer with respect to those assumptions. Next, we'll be talking about verification and validation. Safety verification is the process of evaluating the system capability or the design capability to detect random failures. There are several techniques out there that are used for safety validation. In this slide here, we're showing 4 of them: safety simulation, formal, analytical, structural. Each one of those techniques have different way of reporting results. So in a typical design, you probably need more than one techniques to complete your safety verification. And combining the results between these different methods is not easy, and there's no common or standard way of doing that. The reason we want to combine them is because at the end we want to take one simple output that we can feed it back or back annotate it into the safety analysis tool like FMEDA to calculate the system architecture metrics. So the 2 aspects that we would cover in this working group, one is fields in the data model to support the validation methods, the different validation methods. And second is to propose methods to combine results from those different techniques. We'll discuss next the safety manual. Safety manual is a document that contains all safety aspects about the design. And this is communicated to the consumer so that they can integrate the safety design into their system or their design, include the safety analysis report, the safety features, how to enable the safety features, and assumption of use. However, there's no agreement on the content. I mean, it's left to each company to decide what should go in a safety manual, which can be a problematic if you have to customize your versions of your safety manual for every consumer. It becomes a burden. And there is today mostly the safety manual is done manually, is written manually. So there's no a not clear defined way of automating the content of the safety manual. The actions that this working group are interested in is to define essential information that are needed to be in the manual, in the safety manual, and then identify methods to enable the automation or partially automation of the safety manual from the data model. Next is the safety case. Safety case is an argument that the functional safety is achieved for the design and satisfied by the evidences collected in and compiled in the document. There's inadequate safety argument. There's no agreement, for example, on the format or the language structure. There are diversity of solutions, but none of them enable automation. So the proposed action by this working group is identify languages and a template for the safety case, a proposed solution for the integration from multiple supplier, identify methods for automation, and provide examples on a good examples on a safety case. This is the end of my presentation. I want to thank you for your attention, and I hope you find it useful. Thank you.